Alright, dear children, now we discuss in detail about and we derive the expression of root mean square speed. We also call as RMS, speed of what? Gas molecules. Okay, now in order to derive this relation, let me just tell you that whatever number of molecules present in a gas, okay, the speed of individual molecules, of a gas varies on a wide range. Over a what range? Wide range. That means all the molecules does not move with the same speed. Okay, that means the speed of all the molecules of gas varies in what range? Wide range. That's why if there are certain number of molecules of gas, then every molecule of gas they acquire with a certain speed. That means they move with a certain speed. Okay, so for that we always need to measure the speed, and that is called root mean square speed, also called RMS speed of our gas. Root means the what? Square root. Root means the what? Square root. So this root mean square speed of the gas can be even marked by letter BRMS. B is the velocity speed of the symbol of speed of velocity. So RMS means root mean square speed. So root mean square speed of the gas. So BRMS, that means root mean square speed, can be written by BRMS, and it is equals to square root. Root means square root. Root mean means bar, square velocity of the gas or speed of the gas. Okay, so RMS speed can be always calculated by the formula root. This is called root. This symbol is called root. Mean, this bar symbol means what? Mean square speed, or we also call velocity of the gas. So children, remember this. To measure RMS speed of the gas, we measure by this relation, square root of mean square velocity of the gas or speed of the gas. So out here we need to measure this quantity, mean square speed or velocity of gas, then we take the square root of that measure the root mean square velocity of the gas. Okay, so for that let me just consider there are certain number of molecules of the gas and they all move with a different velocity or different speed. So let me just consider, let B1 comma B2 B3 dot up to Bn. So I am considering this way because I consider there are n molecules of the gas. This n can be of any value. Okay, so but all the molecules have different speed, and the speed are B1 comma B2 comma B3 dot up to Bn, and these are the what? Speed. Okay, these are the speeds okay of n molecules. Let me write this way. The speed of n molecules, okay, of an what gas? Ideal gas. Okay, now if there are n molecules, then all the molecules have a speed. Okay, now this particular relation which I have already written out here, that is BRMS, which is the RMS speed of the gas, is equals to square root of what? Mean square velocity. It's also called mean square velocity. But children, look at this. This can even written this way also. Square root of mean square velocity can be written as B. How many molecules are there? N molecules of the gas, and all the molecules have the speed B1, B2, B3. So I do the square of that. Okay, B1 square plus B2 square dot up to Bn square whole divided by what? N. So children, this mean square velocity inside the square root can also be written this way. Okay, that means sum of the square of the velocity divided by what? The number of molecules of the gas. And this is also called mean square velocity or mean square speed. Okay, but I write this expression of mean square speed or velocity in terms of the pressure, because we know pressure in terms of this square mean square speed or velocity. And you know what is the expression? P equals to 1 by 3 rho mean square velocity. Yes, let me write this expression of pressure in terms of density. So P equals to 1 by 3 rho mean square speed or velocity of the gas. Okay, so I'll make subject from here. If I make subject from here, I'll just cross multiply 3 into P, okay, by rho. Okay, let me bring this in the denominator, equals to mean square speed. See, mean square speed or velocity. So 3P by rho equals to mean square speed or velocity of the gas. Okay, now this value of mean square velocity I put in this expression. So I write down, therefore B RMS is equals to square root. See this square root. Now this quantity is now how much? 3p by what? Rho. So finally see, mean square speed of the gas is given by square root of 3p by rho. So p means pressure, rho means the density. So this is the relation that can be used to measure root mean square speed of the gas, or root mean square velocity also we can call root mean square velocity of the gas. So B RMS equals to square root of 3p by rho. Okay, so important expression which actually need to calculate the RMS speed of the different gases. Okay, now this can be calculated at any condition of temperature and pressure. That's why this relation is a general relation that measures the RMS speed of any gas, whether it's for air, or whether it's hydrogen, whether oxygen or nitrogen, any gas which are ideal gas at any pressure. It can be a normal pressure, it can be the other atmospheric pressure, okay, with a certain value of density of the what? Gas. Alright dear children, now we even write the same expression of root mean square speed in terms of the molecular weight. Just keep in mind the molecular weight of a gas, and also in terms of the absolute temperature, and absolute temperature is marked by letter T, and every gas has molecular weight, and molecular weight is expressed by capital M. Okay, now in order to write the same relation in terms of molecular weight and absolute temperature, okay, I'll take a gas, ideal gas, but of what? 1 mole of ideal gas. So I take 1 mole of what? Ideal gas. Okay, so I write down, let B and T. As you know, B and T are the volume. These are the symbol I am using, volume and absolute temperature. Volume and absolute temperature. Okay, absolute temperature for 1 mole. And you know 1 mole is also called 1 gram molecules. 1 gram molecule, okay, of an ideal gas. 1 gram molecules of an what gas? Ideal gas. Okay. Now, as you know very well that there are the number of molecules present in 1 mole of ideal gas. And that number is called Avogadro's number. So, as you know that the number of molecules in what? 1 mole of a gas is equals to what number? Is equals to Avogadro's number. Avogadro's number. And you know Avogadro's number is actually marked by symbol what? N, capital letter N, and the value of Avogadro's number, as you know, it is 6.02 in 2 decimal place into 10 to the power 23. So this is N, and N is called Avogadro's what? Number. Okay. Now each molecule of gas has a mass also, and that mass we can again write by the same letter M, small letter M, be the mass of each molecule of the gas. Each mass of each molecule of the gas. Each molecule of a gas. Okay. Now if M is the mass of each molecule of gas, then I write down the mass of 1 mole of gas. Okay, the mass of 1 mole molecules. Okay, let me write down, mole. The mass of 1 mole of a gas, okay, is equals to the mass of each molecule of gas into how many molecules are present in 1 mole of the gas? N number of molecules. That is equals to what number? Avogadro's number. So the mass of 1 mole of gas equals to M into what? Capital N. And children, you know that whatever number of molecules are present, whether it's 1 mole or 2 mole or whatever number of molecules are there, they all move with a velocity called mean square velocity. Okay, and again I write in the similar way, let B mean square. So mean square velocity. This is called be the what velocity? Mean square velocity. This is the mean square, okay, velocity of 1 mole of gas. So we are dealing with 1 mole of a gas. Okay. So under this also we can write the pressure. So pressure is same. So pressure P equals to 1/3 of M into capital N. So children, look at it. M into capital N means M into capital N is the mass of 1 mole of gas. Mn is the capital mass of 1 mole of gas. When capital N is the what? Avogadro's number divided by the volume of gas into the mean square speed or velocity. See, mean square speed or velocity. So this is a expression of pressure which can be written in terms of 1 mole of gas. This is for 1 mole of a gas. So we are dealing with what? 1 mole of gas. So what I do now, I just cross multiply. So let me write down P into B. You know, this B I'll take in the left hand side. So it will be PB. And this PB equals to 1 by 3 M into capital N, okay, with mean square velocity. Okay. Now 1 mole of gas has a mass also, and that mass is Mn. So this Mn, as you know, is the mass of 1 mole of a gas. But children, remember this, the mass of 1 mole of any gas is actually equals to the molecular weight of the gas in gram. Is equals to the what? The molecular weight. It is equals to the molecular weight, okay, which is marked by letter M, of a gas. Of a gas in what? Gram. Which means this capital small letter m and n, okay, small letter m into capital N is equals to capital M, where capital M is the what? Molecular weight. So this is true not only with one gas, this is true for any gas. Okay, any what? Gas. So look at this part, I am replacing it. Small m into capital N, the mass of the 1 mole of gas equals to the molecular weight of the gas in gram. Okay, now I replace now this Mn by capital M. So in the relation, so Pb equals to 1/3 of Mn means capital M with mean square velocity. Okay, now Pb equals to 1/3 of Mn mean square velocity. But we are dealing with 1 mole of gas. And you know, for 1 mole of gas, for 1 mole of a gas, Pb is also equals to RT. So look at this part, children. Pb equals to RT, where R is the universal gas constant. So I can write the same Pb, pressure and volume, in terms of temperature, the absolute temperature. And we are actually trying to derive the relation in terms of temperature also. So can I replace Pb by RT? Yes, I write down, instead of Pb, I write down RT. This Pb I write down by RT equals to 1 by 3 M mean square velocity. So from here I'll make mean square velocity as a subject. If I make mean square velocity as a subject, this 3 will go this side. So 3 RT by this M will come in the denominator. So making this as a subject, mean square velocity is now 3 RT by what? M. So from here I can now calculate the pressure. Okay, now we can calculate the what? Pressure. Because we are actually, we can measure the what? RMS velocity or RMS speed. And you know what is the relation? RMS speed is equals to root mean square velocity or root mean square speed. So let me just substitute the value now. Now this quantity is how much? 3 RT by M. So RMS speed or velocity equals to square root of 3 RT by M. So finally, RMS speed or velocity can also be expressed in terms of molecular weight and absolute temperature by the relation 3 RT by what? M. Yes, children, this is another important relation from where you can find numericals also based to calculate RMS speed of the gas, and that is square root of 3 RT by what? M. Okay. Now from this relation I can even write that the RMS speed of the gas is direct proportional to absolute temperature. So RMS speed of a given gas is direct proportional to absolute what? Temperature. So RMS speed is direct proportional to square root of temperature. This means that faster the motion of the molecules of a gas, higher will be the temperature of the gas. Or higher the temperature of the gas, faster is the motion of the molecules of the gas. And this is actually the kinetic interpretation of temperature. Means when I use the word kinetic, the motion is actually based on the temperature. The temperature is one of the factors that makes the molecules of the gas to move faster. Okay, if more increase in temperature, more faster the molecules of the gas move. Okay, that's why the kinetic interpretation of temperatures means RMS speed of the gas is directly proportional to the square root of temperature. Now, children, another thing that we can even make a conclusion from this relation is, if temperature of this gas That means the absolute temperature of the gas is 0. If T is 0 means absolute temperature of the gas is 0. Then what happens? This BRMS velocity also becomes 0. Now BRMS velocity 0 means the molecules of its motion. So the motion of its molecules of a gas will cease. Means the molecules are not in a state of motion. The molecules will simply stop. All the molecules of gas will simply cease. Means no motion occurred by the molecules at all. But this is not a reality. This cannot actually happens in actual practice. Now, absolute 0 temperature means T0 means minus 273 degrees Celsius 0 Kelvin. Okay. So according to kinetic theory, absolute 0 is that temperature at which the motion of all the molecules of the gas stops. That means motion of all the molecules of gas stop only at absolute 0 temperature. Okay. But this is not a actual practice. This is only a theoretical consideration. That's why it is also clear that absolute temperature can never be possible. Okay, can never occurs. Okay, that's why absolute temperature, and I'll tell you, absolute temperature is a temperature which can never be negative also. Absolute temperature means the lowest temperature, that is 0 Kelvin, and after that the temperature cannot reach less than that also. Okay, that means absolute temperature can never be negative. That's why this BRMS speed can never be negative. If temperature cannot be negative means speed cannot be negative. Thus, no temperature is possible below absolute 0. Means below absolute 0, temperature cannot be considered at all. But even this absolute 0 is the temperature of a gas which cannot actually achieve. This is only a theoretical consideration. So this is the relation that measures the RMS speed of the gas in terms of the molecular weight and absolute temperature of the gas.